So let's start with an analogy. What I would like to see is that what is happening right now with big data and the librarian, both information and library sciences, and how things are changing towards in the future. So I'll start with a simple analogy first, and then try to see how we can go from there to the role being played by big data in our lives. So what is this? Anybody know what is this? Yeah. So this is basically used for? Yeah. And we use that all the time, and sometimes we may juggle balls, maybe 3 or 4 of them at a time, based on the importance of things are happening. We are all librarians, we are an information scientists, we know how to juggle balls in there. And sometimes we do a little bit more extra by having it like going on a very unstable platforms, we all know about that, and then how to juggle things to work on that. So this is where we are currently, in a sense, trying to do things, but things are going far away. We are going to deal with something entirely different, something which can kill us, in a sense. So ILS today is just a few balls, maybe 3 of them, trying to do that. And then maybe a little bit more. Some more people are doing a little bit extra with 3 or 4, and then maybe 5. Okay, that's where we are at this particular stage. But as we go towards tomorrow, as more and more science data come in, and more data from the web and sensors and all those things come in, things are going to change. We are not dealing with just juggling balls here. We are dealing with different kinds of data. We are dealing with different kinds of material, like in this particular case, juggling with something simple as tennis rackets. But then we have to work with each other. So that is also another revolution coming in. You are not going to do it by yourself. You need to work with a lot of other people. Integration, federation, whatever we're going to call it, is going to be their part and parcel of our life. And then we need to juggle the balls so that we are all played together and you catch somebody else's balls all the time. And then we need to deal with sensitive things also, things which can burn us. We need to be very careful. Privacy and security and data which are going to be like medical data and even research data. When we are dealing with, we need to be very careful about how we provide access to that and how we store it and how we make sure that it is not compromised. And we need to deal with something beyond that, not only with other people working together, but people who are juggling different things and are relying on us while we are juggling our own things to be stable so that they can juggle on top of us. And sometimes they drop something, you catch it, and then you need to throw them back to them. So it is a very complicated thing which is happening. And individually also, as a personal life, you are having a lot more data coming to your life. Not just as a librarian, but as a citizen. You have a lot of things coming at you. Used to be a very simple thing, trying to go to the doctor and come back. Nowadays, it is not like that. You have to deal with a lot of things before you go there, probably fill forms and take them along with you and then give it to them. And most of them are becoming online nowadays. You do that at home before you even go to the doctor, type of things. And the final thing is that you got multiple things coming in, different kinds of data, different kinds of things, all coming together. Everything is becoming harder and harder and harder. And that's where we are going towards the ILS tomorrow. So we are at a cusp. We are standing, having all these things to juggle with and don't know what to do with it. We got rings to juggle, we got these bailing pins to juggle, we have knives and firebrands and stuff like that. We don't know how to deal with it. But if we don't do a good job, we are going to drop the ball. And this is not any ball, this is our own earth, in a sense, if you don't deal with all the sensitive data and how it is being done, and we need to make sure that information is already available and we deal with it properly. So that provides you with a sense of starting with a few balls, juggling with it, and juggling the whole world in your hand. And we are the main people in there, in a sense. The information and library science plays a large role, a larger than role than even the scientists are playing, because we are the substrate at which data exchange is going to happen, and we need to make sure that we know what we are doing. So that gives you an idea about where we are going. So let's look at what type of data are involved. We have heard about big data all the time. If you pick up any paper, any of the things from Scientific American to Nature to Science, anything you take it, you see that they are talking about big data. NSF, White House, everybody has a lot of white papers and proceedings and things like that coming out of it. The conferences are being held about that. So what is it all about? It is because the amount of data which is coming in is becoming overwhelming. Used to be that we get a few megabytes, gigabytes of data and things like that. And people started talking about, terabytes of data. You can buy a terabyte of disk today at around $50 and things like that. But terabytes of data is already passé. We are talking about petabytes, which is 1,000 terabytes. We are talking about exabyte, etabytes. We are going up and up and up type of things. There are supercomputers which are built basically with RAM, which is the random access memory, or in-memory systems, which are in order of hundreds of terabytes. Nobody even thought about those type of things just 5 years back, that these type of things can happen, and things at that level are happening in there. So the type of data we are going to deal with, web data, which is overwhelming again and again. With the number of websites which are growing, and scientific websites are being available to everybody so that you can get to different types of data. Even though the most sensitive data is still not available, a lot of processed data is available for everybody to use. E-commerce is another sensitive area, and a lot of different scientific projects, such as the Light Hadron Collider, LHC, is producing data at a very fast rate. LSST is another telescope which is coming up, which is going to bring about a whole bunch of revolution. It's going to talk about petabytes of data per day type of things that are coming out in there. And social networking data, the data which we do all the time. Big data is not just made by scientists and projects and instruments, it is also made by people. So one of the biggest growth is happening in social networks like Flickr, Twitter, Facebook. All those type of things are becoming larger and larger, and trying to glean information out of that, and trying to take the data, convert them into information, and take that information and convert them into knowledge is the process which need to be done in there. For example, one of the anecdotes which everybody says is that people knew about the spread of diseases by looking at how the Twitter feeds are coming in, by studying Twitter feeds faster than CDC can tell that this type of epidemic is happening. Okay. This has happened in multiple cases all over the world about spread of diseases in Haiti and other places. They were able to do that just by analyzing the Twitter feeds. So data analysts are becoming more important, and trying to work with them is probably one of the biggest challenges which we are going to face. And I don't need to talk about medical and health information. We are in a place where such things are common and normal. How much of data? I have some numbers here, and don't take it with a pinch of salt. These are really, really old numbers. Things have changed possibly an order of magnitude, and probably 2 or 3 orders of magnitude in some cases. Okay, but just to give you an idea about where we are going comparatively, or where we were just 3-4 years back. Okay, in 2008, Google was processing only 20 petabytes of data a day. Currently, they are doing at 200 petabytes of data a day type of thing. And similarly, if you look at eBay, was doing like 6 to 7 petabytes of user data of the type of things which are coming in. Currently, they are doing an order of magnitude about that. And CERN, the Large Hadron Collider, is generating more than 15 petabytes of data per year. It is not just the data which is coming out, but the secondary data which is coming in, and how to deal with it from with these secondary data and provide it to the scientists so that they can make a sense. There are some differences also. I normally, when I give this particular slide, I also say that there is a difference between what Facebook does and what CERN does. One of the things you can talk about Facebook is that multiple people are creating the data, and the data is going to a centralized place like the Facebook repository. Even though it is not centralized, it's like multiple Facebook repositories, mirror images, and stuff like that, where it goes in, but it is like several millions of people or several millions of feeds going into Facebook, like Twitter or Facebook and things like that are going in there. Whereas in CERN, it is the other way around. These 15 petabytes of data is just generated in one place, which is spread out over there. So you can see the logistics of these two types of data movement is entirely different in there. We have seen that. If you're using your your wireless at home and trying to use maybe the cable company and things like that, incoming is faster, outgoing is slower. So things change. They are not exactly the same. So trying to say the 15 petabytes per year from LHC is harder than 2.5 petabytes of data or 30 terabytes of data per day or 2.5 petabytes of user data is harder. It's comparatively really different, and each has its own challenges, and we need to deal with it. So when we talk about big data, we normally talk about at a very high level, what type of things are there? And when somebody says big data, what comes to mind first? Sorry, I'm a professor, so I always ask questions. What comes to mind first when I say big data? Volume. What else? That is probably the only thing most people understand. When I say big, they think big is just volume. Volume is one of them. Okay? It is an exponential increase in size and count. Like I said, we are going from petabytes to terabytes to petabytes to exabytes, etabytes, and all those things type of thing. Zettabytes, all those things are happening in there. But there are other things which are coming in also. Velocity. How fast is this data being created? And you need to analyze it at the same time. For example, take financial data. If I don't analyze it in the next microsecond, I may lose a trade. So I need to do that in that particular type of things. Similarly, when you're trying to deal with medical data, that's what is happening. You want to analyze the data coming from multiple sensors from the patient so that you may be able to immediately diagnose that something bad is going to happen in the next few minutes. You want to do that. Same thing with seismology. Seismic data coming in from tens of thousands of sensors need to be analyzed so that you can predict where the waves are going to go whenever an earthquake happens. Even though these things are not easy, and most of the predictions happening in the seismic world is in the order of seconds. You don't get more than that. But even giving a few seconds of time for people to get out of the building is more than enough to deal with it, type of thing. So that is the type of velocity we are working at. So volume itself is not a criteria, but how fast is the data is created. And the third one, which probably is another one which we never think of, is the variety of data which need to be worried about. Okay. Different formats. Every instrument provides data, and each instrument has its own idiosyncratic metadata attached to it. Okay. We all deal with metadata. Okay. But even in metadata, there are no standards. Even in data, there are no standards. The way they are coming up, you need to worry about how am I going to deal with it. Like you take MRI, coming from instruments, MRI data, magnetic resonance imaging. Two machines developed by two different companies will not have the same type of format for them. Even more problematic is that the same company might have two machines, two generations of machines, and they don't have the same format. So if you are a person who is processing this data, you need to worry about what format it is coming in, how do I convert into a common format, or how do I deal with it in a particular format and come to it. Do you want to lose data when you're converting? No, you don't want to do that. You still want to deal with it to do that. How do I do the arrangement of these type of data? It's again a big problem. Things are coming from multiple places, from multiple people. How do I pull them together so that I can make sense out of it? I can make some knowledge out of that one. So that is the main thing. The fourth one is the fidelity of the data. When everybody is a data producer, who is going to tell that whose data is better, whose data is correct, whose data is something which we can rely on? Okay, that is where the problem comes in. Again, librarians are very important in this particular one because we are known as the authority. You go to the library, you get a book, you know that the book is right. You go to a library, get a journal article from their archives, you know exactly that that is the correct journal article. Nobody changed anything in there. Okay? That is the type of fidelity is needed, and currently when you talk about big data, that is one of the biggest problems. It is not the volume, it is not the velocity, it's not the variety, it is the veracity of the data, of how can I rely on this particular data to make sense out of that. If I can have 4 sources coming in, of these 3 are reliable and 1 is unreliable, how do I make sense of that one? How do I know which one is unreliable? And things keep on moving. Something which is reliable today may not be reliable tomorrow. We are not even talking about human-produced data. This can be data produced by a sensor instrument, which might have gone haywire. And then you're getting some data and you don't know what is wrong with it. And you still rely on it and take some calculations and get into problems. And finally, the last one they talk about in big data is value. That the main reason the big data is there is, it is there is not important. What kind of value does it give it to you so that you can convert the data into a knowledge? And how do we do that is there. And that is where the data analytics comes in. How do you analyze the data to get more information out of that, more knowledge out of that, and integrate multiple data together and get value out of that? So that is where the integration, the federation, and multidimensional analysis plays a major role in big data. So when we talk at this particular level, there is a big paradigm shift which is happening. This has been happening over the past 4 or 5 years. Okay? If you ask about maybe around 2005, 2006, people were still talking about supercomputers as the big things in there, because there are a lot of computation need to be done, and you would like to have these supercomputers all sitting in one large room, maybe as big, the computers as big as this room being in there, and things like that, and larger than that. I used to work in a supercomputer center back in San Diego, but now things are moving. Things are becoming more data intensive. And that has become a big paradigm shift in there. So instead of trying to do the computation, you are now doing data analytics. The big difference is that most of the computers currently, supercomputers, laptop, or anything, are more geared towards how to do the computation. The computation is more from outside, from the network, into the CPU, or the computing processing unit, central processing unit, is the hard part. So when you go into data intensive computing, you need to worry at that particular level, how am I going to bridge that gap so that it can be done? So again, compute intensive has a lot more easier work than the data intensive type of thing which we are trying to do. And another one, data is not in one place. Data is too large. You cannot move it. It is in one place here, maybe a data repository in New England, and you have a supercomputer in San Diego. Try to move the data from New England over there. It's going to take maybe several Federal Express trucks to do that. You don't even try to do it over the wire. It's not even possible. So you need to just put it in a truck and send it over there. That is the way large data gets transferred even today, type of thing. Even with a lot, light and dark fiber, light fiber, and things like that, still we have the same problem. The second thing which is paradigm shift which is happening is that used to be that you take a little amount of data, use modeling, use a lot of computational power to do large actions on small data. That was the paradigm which was happening. When you're trying to do chemical modeling and things like that, that's how you do it. When you're trying to do the simulation of, say, how the Big Bang occurred, that's how you're going to do it. If you're going to do seismic wave propagation simulation, that's how you do that. In physics, in chemistry, and any of the fields, environmental sciences, that's how you do it. Ocean current modeling and things like that. You take a small amount of data and fit a model to that and then see it is there. But nowadays, you got a large amount of data coming from multiple sensors, and you do what is called small actions on them and try to aggregate those actions into bigger and bigger actions to come to that. So the model of computing has completely changed from doing a large amount of, like several hours of compute, several days of compute time on a supercomputers, than to small amount of work in a network of computers to do that. And the other thing which is happening, because of the size of the data being pretty large, you move the data. Rather than, you used to be, you move the data to the processing site, now you move the process to the data site. And that's how things are happening right now. And the two types of model which are there, the supercomputer model and the map-reduce model, are the two paradigm shifts which are happening. If you know how Google works, they use the map-reduce model. When they talk about they are dealing with petabytes of data and giving you answers in a second or microsecond and things like that, because they do a lot of data-intensive processing, and the data is spread out into thousands and tens of thousands of computers, and then you do the processing at that particular level. And again, another paradigm shift which is occurring, people are not even realizing that, is that it is becoming from a function-oriented chaining of ways of doing things to what is called service chaining. There is, if you look at the old way of doing computation, it used to be tightly coupled. You write code and code libraries and code calls another code and stuff like that. Now it is all, you try to find out services, and you try to loosely couple those services to do your work. So that is another paradigm shift which is happening. And finally, what is all leading this is that we are doing what is called database science rather than model-based science. People don't think about models of, let us say, the climate model, and try to see if the climate model simulation meets what is we see in real world sensors, data, and things like that. It is the other way around. You just don't even do the modeling. You just take the data and see what the data is coming up with the answers. Happening very much in the genomic sciences. How do you think people are finding disease genes which are associated with diseases? There is no model or something like that. Just by doing raw data comparisons, trying to figure out how they map into each other, pattern matching at that particular level, and trying to do that. So the model is, the way we do the things is from models to database sciences. Again, when you talk about these type of things, organizing the data is very important. If you don't organize the data, you don't know how the value of the data, the veracity of the data, and how fast you can do with this type of computation, you get into trouble. Okay? So where do we stand as information scientists, as librarians in this particular one? I've been working in this area for nearly 15 years in big data. As a scientist, as a computer scientist, first I put a computer scientist head, and then I put an applied science person head, worked with all sorts of domain science people in helping them with their big data problem. Now I put on my information science, library science hat, and then work with people to do the same thing. So I have been wearing multiple hats in the past 15, 20 years dealing with that particular one. Like when Elaine was telling about that, I did a book on what do you call the semantics of digital disjunctive logic program. That is highly theoretical work. Nobody will use it. I can tell you that. It's probably in all the libraries for all I know. Type of thing. So that is a highly theoretical work which parts of it are being used now in what we are doing, but not at a very big sense. I lost my, nope, sorry. How do we go back? Sorry about that, it moved multiple things. Okay, there we are. So I look at it to see what type of things are needed for big data, for us to play a role in big data. And in my experience, these are the type of things which are needed for big data to succeed. Organization of the data is important, because until you organize, you won't be able to discover it. How do you classify it? How do you write metadata? Metadata is really, really important. You can have data, you don't have metadata, it has become completely useless type of thing. how does the, okay, you know the web was there in the early 90s. How many of you used the web in the early 90s, like 92, 93? How did you use it? How did you find a website? Gopher, yeah, even before, this is after Gopher, the web. You find it by going to the Mosaic, and they have a drop-down menu called cool sites, the new sites. That's how you used to find it. So because there are only hundreds and hundreds of sites, not even thousands. You need to go there to find it. When you have hundreds of millions of web pages and websites, how do you find them now? How do you find something in the web now? Search engines. Google is what we say, but it's search engines. Okay, Google is one of them, probably the very best, which is available right now. But there are other search engines which are particular to your own domain. So if you are a medical scientist, you probably don't go to Google. You probably go to PubMed to do that. Search engines are the things which are happening in there. So what is a search engine? It is providing some sort of a metadata to you that this website or web page contains these data. Obviously, it is not doing a great job because it is doing at a very lowest level. The least of the level is just by saying that this word occurs in this, nothing more than that. Even though they do some fancy footwork in trying to find out the best answer for you and things like that, the bottom line is that this word is occurring in this web page. So when you ask for jackal, I'm going to give you everything which has jackal occurring in there. Okay, that is the type of things they do, but we can do better than that. And scientific data is not good at all for Google type of search. You need to go beyond that to do that. So you can see that where we play a big role. Retrieval is another one, information retrieval. From what we've been doing at the level of physical books to digital artifacts and now to scientific data, information retrieval is going to completely change the way we do it at all. Because it's not keyword search any longer. You cannot do that. You cannot do faceted search, no more. Okay, you need to go beyond keyword search and faceted search. But still, the concept is the same. Information retrieval is information retrieval, and all the things which we deal with at the normal keyword level or the card, the library card level and things like that is the same thing which is going to come in there. Somebody has to do the legwork to make it available, and who are the people who are going to do that? Okay, it's not the scientists. They generate the data. They don't want to do the legwork for that. They don't do science. But sharing, somebody else has to do that. That is where the information science people come in to help in taking their data, trying to do something with it, and giving it to others. It is like that, right? And during the olden days, authors write books, but authors are not librarians. They don't distribute the books. Somebody else tries to take it. This is the title. This is the author. These are the keywords. These are the subject. All these things are made by the librarians and put in there. And we have the same type of roles in there. And privacy, security, again, integrity comes into the picture. How do we deal with it? Type of thing. And these are all the things which we have learned, which we have been dealing with on a normal scale, and the things hasn't changed at all. Even for tomorrow, it's going to be there. All these things are there. But the main problem is we need new methodologies, new way of thinking, new way of processing, and new way of interacting is what we need. But the basic underlying concepts are exactly the same. So the future is bright. And we need to move forward, learn new things, but apply the old principles in dealing with it. So this is my first part of the talk.